Let's try to solve this problem here. A sphere of mass 5 kg is tied to an inelastic string. So this string here, it's a string that cannot be stretched or it cannot be compressed. The length is fixed. Okay, you have a mass of 5 kg. Let's label it. This mass here is 5 kg. Okay, it moves in the vertical circle of radius 55 cm. So this circular motion here has a radius of 55 cm equivalent to 0.55 meter. At a constant speed of 3 meter per second, so means by throughout this journey over here, the speed is constant at 3 meter per second, as shown in the figure above. By the aid of the free body diagram, okay, so you need to sketch a free body diagram for this question, determine the tension in the string at point A, point D, and point E. Okay, I think you're able to deduce that at point A, at point D, and point E, all 3 points here, they will have different free body diagram because the tension are pointing in different direction. So I believe for each of the question, you need to sketch a new free body diagram, and based on the free body diagram, you determine the tension in the string. Okay, we will still follow through the same 4-step sequence that we discussed in chapter 3, Dynamics of Linear Motion. We will start by sketching a free body diagram, followed by resolving the force. Then after we resolve the force, we check whether each axis is in equilibrium or not in equilibrium to choose whether we use Newton's first law or Newton's second law to solve the problem. Then lastly, we proceed to solve the problem. Okay, so let's follow through these 4 steps for each of the question. Let's start with question A, which is on point A. Okay, so point A, we'll sketch a free body diagram for the sphere. So we sketch our dot to represent the sphere, and we have our axis, not rotated, just a normal conventional axis. Okay, so for this sphere over here, because it has mass, therefore it will have weight. Okay, continue. Because this mass over here is connected to a string to the center of the circular motion, there will be tension. So tension will be away from the object. Because A is over here, away of the object, along the string must be pointing downward. So there will be a tension pointing downward as well. Okay, is there any force being explicitly mentioned in the question or in the diagram? No. Is there any contact surface for sphere A? Is sphere A touching anything? No. So if it's not touching anything, then the question of whether it's rough or smooth surface is irrelevant anymore. So we ask ourselves the 5 questions, and these are the only 2 forces available for the free body diagram of the sphere at point A. So we are done with free body diagram. Let's move to step 2, where we resolve the free body diagram. If you look at this free body diagram over here, the only 2 forces we have here are in the y-axis. So they don't need to be resolved anymore because they are on the axis itself. So we may skip step 2 and proceed to step 3. For step 3, we check whether each axis is in equilibrium or not in equilibrium. If it's in equilibrium, we solve it using sum of f equals to 0. If it's not in equilibrium, we'll solve it using sum of f is equals to ma. Okay, so you can see that for the x-axis over here, there's no forces acting in the x-axis. So we know that in the x-axis, the forces are definitely in balance. Okay, there's no force, so sum of f must be equal to 0 for x. Okay, so let's write down. For x, it's in equilibrium. So if you choose to analyze it, which we don't need to analyze because there's no force, you can analyze it using sum of fx is equal to 0. Okay, how about the y? We know that in the y-axis, you have this object here moving in a circular motion. So in the y-axis, there's definitely a centripetal acceleration that is pointing towards the center of the circle. Center of the circle. Center of the circle. Always pointing towards the center of the circle. Okay, because it's always pointing towards the center of the circle, therefore, you know that in the situation at point A, there will be acceleration pointing downward. Okay, so for y-axis, there will be acceleration pointing downward. Okay, so for y-axis, you know for sure that it is not in equilibrium because there is acceleration. To be more specific, there is centripetal acceleration. So you need to solve it using sum of fy is equals to may. Okay, so once we are clear which axis is in equilibrium, which axis is not, we can proceed to solve the problem. So let's solve the problem. We don't need to analyze x because there's no forces in x. Let's just analyze y only. Okay, sum of Fy is equals to MAY. Okay, so to see which force is positive, which force is negative, forces that follow the direction of acceleration, we consider it as positive. Forces that goes in the opposite direction as the acceleration, we consider it as negative. So for this situation over here, both the tension and the weight are in the same direction as the centripetal acceleration. Therefore, we can consider both the tension and the weight to be positive. So I can say positive tension plus weight is equals to MAY. MAY over here, because we know that the acceleration in the y direction is actually a centripetal acceleration, we can change it to become centripetal acceleration. That's fine. Okay, then later you need to select whether you want to change the centripetal acceleration to be r omega squared, or you want to change it to become v squared over r. This one you have to make a choice, but I believe the choice is clear. We are going to take v squared over r because we have v, we don't have omega. So later we will not be using r omega squared, we'll be using v squared over r. Okay, so if this is clear, we may proceed to do some rearrangement. T plus mg is equals to mv squared over r. Therefore, we can shift the equation to become T is equals to mv squared over r minus mg. Okay, so I think it's just a direct substitution because we have all the values we need here. So mass is 5 kg, the speed is 3 meters per second square, divided by r. R is the radius 0.55 minus mass is 5 kg, your gravitational acceleration is 9.81. So if you calculate everything slowly and carefully, I believe you'll get the answer of 32.8 Newton for the tension when the sphere is at point A. So when the sphere is over here, the string is pulling on the sphere A with a tension of 32.8 Newton. Okay, so once we are done with this question, we can proceed to the next point, which is point D. So let's continue. For question B, point D, again we have our free body diagram. Every new location requires a new free body diagram because our rope is in different direction. Okay, we still have our weight because the object has mass, but now because the tension, because the string is horizontal right now, for at point D, the string is horizontal, so tension away from the object will be to the left. Okay, so we have our tension pointing to the left right now. Okay, so this is our free body diagram because there's no contact surface, there's no smooth or rough surface to be considered over here. So we are done with our free body diagram. Let's proceed to resolve, but we see that there's nothing to resolve because every forces are on the axis right now. Let's proceed to step 3, which is in equilibrium or not. Let's check for x. For x, we see that there's only one force in the free body diagram. So you can know that the left is definitely not balanced by the right. So definitely this is not in equilibrium. But at the same time, we see that the centripetal acceleration is pointing to the left. So you're 100% sure that in the x-axis there will be acceleration. Okay, so for the x-axis, you may say that it is not in equilibrium. Therefore, you may state that sum of fx is equals to max. And to be more specific, this ax here will be the centripetal acceleration. Okay, how about y? This is where it gets a bit complicated, and this is why this question is actually illogical. Okay, so you can pay some attention here. For y over here, you may see that the axis over here, there's only one force, which is the weight. And this means that our y-axis here, it's impossible for the forces to be in equilibrium. The force cannot balance and cancel each other out. Because of that, we should definitely say that it is not in equilibrium. Okay, but that will mean by the sum of Fy will be equals to MAY. So if there's a MAY, and this AY here means that there is an acceleration. So there must be a change in velocity. And to be more specific here, because our acceleration must be pointing downwards, the same direction as the net force in the y-axis. The net force in the y-axis is pointing downwards. we know for sure that there must be an acceleration that points downward as well. This is a must, okay? Because you have a net force, it has to be there has to be an acceleration. But this means that the acceleration at point D is also pointing downwards as well. There's another acceleration AY that is pointing downwards. If we see that there is an AY that is pointing downwards, this means that there's an acceleration that is pointing in the opposite direction as the velocity. Okay, now the velocity is pointing upwards, but we have an acceleration pointing in the opposite direction, which is pointing downwards. Both of these vectors are in opposite direction, and we learned from kinematics last time that if the acceleration and the velocity are in opposite direction, what happened is, this is quite interesting. What happened is, because they are in opposite direction, it will cause the object to slow down. Okay, we learned before that if the acceleration and the velocity same direction, you speed up, opposite direction, you slow down. So now because they're in opposite direction, they will slow down. But we see that this question here says that it moves in the vertical circle of radius 55 cm at a constant speed. This is impossible to be done for a vertical circular motion like this. It's impossible to be done because there's acceleration in the axis over here. This means by at this point, the object must slow down. Because it slowed down, it cannot remain at a constant speed. That's why this question here is actually illogical. But I'll still discuss this question, I'll still finish this question because it's still a kind of popular question for this chapter, but it's actually an illogical question. Okay, so I'll still continue to discuss, and I am going to assume that it's incorrect to assume this, but I'm going to assume that we are going to analyze it as sum of Fy equals to 0. That means by the force unbalanced, that's why there's no change in velocity. No change in speed, sorry. Wrong assumption, but forced to do so in order to solve this problem. Okay, so next time when you see a question that happens like this, you know that there's an acceleration in the same direction or opposite the direction or tangential to the path. If you see an acceleration that is tangential to the circular path, you know that this is not in your syllabus actually, because your syllabus can only ask questions which involve uniform circular motion, where the object moves in circular motion with constant speed. But in this case, this is not the correct situation. Okay, let's don't talk too much about this. Let's continue to solve the question. Okay, so we'll analyze only the x-axis, where sum of fx is equals to mex. What we have here is only tension. So tension is equals to mac, but we will change the centripetal acceleration to become v squared over r. So now this is just a simple substitution once again. Mass is 5 kg. The speed is 3 square divided by r. R is 0.55. So now if you calculate your tension, I believe you get an answer of 81.8 Newton. Okay, so you see that you need a greater tension to pull onto the sphere when the sphere is at point D. Okay, you need a greater pull compared to previously when the sphere is at the top. At the top, you don't need that much pull, but when you're at point D, you need a stronger pull. Okay, let's move on to question C, point E. At point E, let's again sketch a free body diagram. Okay, you have your weight pointing downwards. Okay, weight pointing downwards because this object here has mass, but at the same time you know that there's a pull pulling upwards towards the center of the circle, so there will be tension as well. Okay, so this will be the two forces acting on the sphere when the sphere is at point E. But we know that because the acceleration is always pointing towards the center of the circle, the centripetal acceleration will be pointing upwards at point E. Okay, so for the free body diagram, you know that there will be centripetal acceleration pointing outwards. Okay, so now we are done with the free body diagram. The next step will be resolve, but there's no forces to be resolved, so we skip to the next step, which is the in equilibrium or not. Okay, for x-axis there's no forces, definitely in equilibrium. So because it's in equilibrium, we will use sum of fx equals to 0 if you want to analyze the x-axis. For the y-axis, you know that there is an acceleration already, so it's definitely not in equilibrium. And because it is not in equilibrium, we will definitely be using sum of fy is equals to may. Okay, so once we are done with this, we may proceed to analyze only the y-axis only. So sum of fy is equals to may. So there are two forces in the free body diagram. We'll take the forces in the same direction as acceleration as positive, so tension will be positive. We will take the forces in the opposite direction of acceleration to be negative, so the weight here will be negative. So T minus W to be equals to may. So right now we can write it as tension minus mg is equals to may. And a bit of rearrangement, you get may plus g. Okay, so do your substitution. You put 5 kg, your centripetal acceleration. Oops, I think I missed out something. Okay, let me change a bit. This one will need to be changed to become the centripetal acceleration, and centripetal acceleration is v squared over r. Okay, so this will be 3.0 square over r 0.55 plus 9.81. Okay, so if you proceed to do your calculation, you get the tension. I think it's a even larger value, 131 Newton. So that means when the sphere reached the bottom of the circular path, the pull exerted by the rope over here will be even larger than all the other points before this. So it will be a very mild pull, but the pull gets greater and greater until you reach the bottom where the pull reached the maximum, which is 131 Newton. Okay, so this is how we find the tension of the string at different position during a vertical circular motion. But as I mentioned earlier, this is an question that is impossible to be done because for vertical circular motion like this, you cannot keep the speed constant. And for our syllabus, we'll only be analyzing circular motion where the speed is constant. So it's our syllabus, but I will still discuss it like what you see here right now. Thank you very much.